Have you ever stopped to think about what powers both the battery in your phone and the nerve impulses in your own brain? It's the same invisible force, electrochemistry. And today, we're going to pull back the curtain and see how it all works.
I know. It sounds like the start of a really weird joke, right? But the answer is actually the key to understanding how we generate and store electrical power using chemistry. This bizarre biological twitch, first seen centuries ago, literally sparked a revolution.
So the story really gets going with these pioneers. Back in the 1780s, Luigi Galvani's experiments with frogs led him to believe in something he called animal electricity. But then Alessandro Volta came along and said, hold on a minute, I don't think the electricity is coming from the frog. I think it's the metals. And that one insight led him to invent the very first battery in 1800. After that, scientific giants like Michael Faraday and Walther Nernst built on that work, giving us the fundamental laws that turned a curious accident into a full-blown science.
All right, so here's our game plan. We'll start with that initial spark of discovery, then we'll check out how electricity travels through liquids, no wires needed. From there, we'll get into the rules of that flow, zoom in on where the action happens at the electrodes, and finally, we'll put all the pieces together and build a simple battery.
First up, a spark of discovery. We're heading back to the very beginning, to a moment where a complete accident opened up an entire new world for science.
And this is the moment. Seriously, it all started right here. Galvani was just doing his thing, dissecting a frog, when he saw its leg twitch when it was touched by two different metals. That one single, totally accidental event was the catalyst. It got scientists everywhere thinking, what is this invisible force, and how can we put it to work? Which leads us to our next big question. Electricity's liquid highway. We all get how electricity zips through a metal wire. But a battery? That's full of, well, liquid. So how does a current get through that? Turns out it's a completely different kind of electrical flow. Okay, so here's the big difference, and it's super important. In a solid wire, what we call electricity is really just a river of tiny, tiny electrons moving. But in a liquid, the charge is actually carried by these much bigger, bulkier things called ions. You can think of them as atoms that have either gained or lost an electron, giving them a charge. The current is literally a flow of these charged particles. And the special ingredient that makes this all possible is called an electrolyte. When you dissolve an electrolyte in something like water, it breaks apart into those free-moving ions we were just talking about. That's what creates a solution that can actually conduct electricity. Bottom line, no ions, no current. But, not all electrolytes are created equal. You have strong electrolytes like regular table salt. You drop it in water and bam, it completely breaks apart, flooding the solution with ions. Then you have weak electrolytes like the acetic acid you'd find in vinegar. They're a bit more hesitant. Only some of the molecules break apart, which means fewer charge carriers and, naturally, lower conductivity. Okay, so this brings us to the next logical step, the rules of electrical flow. Now that we know what's flowing, let's figure out how we can measure and understand how well it flows. We measure this flow using two key ideas, resistance and its total opposite, conductance. And it works pretty much the same way in a liquid as it does in a solid wire. The resistance depends on how far the current has to travel and how much space it has to move through. So the lower the resistance, the higher the conductance, and the better that solution is at carrying a current. So what actually determines this conductivity? Well, it really boils down to three main things. First, the nature of the electrolyte itself. Is it strong or weak? Second, the concentration of ions. How crowded is it in there? And third, the temperature of the whole solution. Now, this is where it gets really interesting. You'd think that adding more and more electrolyte would just make it more and more conductive, right? Well, yes, but only up to a point. After that, something weird happens. The conductivity actually starts to drop. And why? You literally get an ion traffic jam. The solution gets so crowded that the ions start bumping into each other and getting in each other's way, which slows the whole flow down. Temperature, on the other hand, is way more straightforward. As you can see from the data, as you heat the solution up, the conductivity goes up with it. It makes sense, right? You add heat, you give the ions more energy, they start zipping around faster, and they carry charge more efficiently. Okay, so we've got the liquid highway figured out. But where does the actual chemistry happen? Where does the spark get created? That brings us to the most critical part of the whole setup, the electrodes. This is the reaction zone, the place where the world of chemistry meets the world of electricity. This is where the magic happens. So what is an electrode? Honestly, it's pretty simple.
It's just a conductor, usually a piece of metal, that you stick into the electrolyte. Its whole job is to be the on-ramp and off-ramp, the gateway for electricity to either enter or leave the solution and kick off those chemical reactions. Now get this, because something amazing happens right at the surface where the metal meets the liquid. Think of it like a super busy border crossing. You've got metal atoms from the electrode deciding to jump ship, leave some electrons behind, and become positive ions in the solution. At the exact same time, you have ions from the solution coming over, grabbing some electrons and becoming neutral atoms on the metal. This constant back and forth creates this charged up zone right at the border, what we call the electrical double layer. And that separation of charge, that constant push and pull between atoms becoming ions and ions becoming atoms, that creates an electrical pressure. And that, my friends, is what we call voltage. Or, to be a bit more technical, the electrode potential. It's the natural tendency of that specific material to either push electrons out or pull them in. All right, it's time for the grand finale. We've gathered all the ingredients, we understand all the concepts, let's put them together and build ourselves a battery. We're going to assemble what's called a galvanic cell. And there it is. This is basically it, the great-great-grandfather of every battery you've ever used. We have two different electrodes, in this case, a strip of zinc and a special reference electrode, and each one is sitting in its own little bath of electrolyte. They're connected up top by a wire, and that little U-shaped tube in the middle, that's a salt bridge. Its only job is to let ions travel between the two sides to keep everything electrically balanced. So how does this thing actually work? It's like a four-step dance. Step 1, over at the zinc electrode, which we call the anode, zinc atoms willingly give up their electrons and dissolve into the solution as ions. Step 2, those freed up electrons get pushed out and start traveling through the wire. Step 3, they arrive at the other electrode, the cathode, where they're immediately scooped up by hydrogen ions, forming hydrogen gas. And finally, step 4, the salt bridge completes the circuit by letting other ions flow between the two halves, which prevents any charge from building up and stopping the whole process.
Now, if you were to hook up a voltmeter to this exact circuit, this is the number you'd see, negative 0.76 volts. This is the standard electropotential of zinc. It's basically a score that measures how strongly zinc wants to push its electrons away compared to our standard, which is hydrogen. That negative sign tells us that zinc is way more eager to give up its electrons.
And that right there, that is the fundamental secret to every single chemical battery ever made, from the huge lead-acid one in your car to the tiny lithium-ion one in your phone. So the crucial point is this. You just take two different materials with different potentials, connect them, and the difference in their chemical push forces electrons to flow in one direction. You've just created electricity from pure chemistry. Think about it. We went from a twitching frog's leg all the way to the battery that's literally powering the device you're using to watch this. It's a perfect story of how a little bit of scientific curiosity can reveal a fundamental force of nature and completely change the world. It really makes you wonder, doesn't it? If we can harness this invisible chemical push to power a light bulb, what other invisible forces are just out there, waiting for their own happy accident, ready to be